In this presentation, and we're doing this here in our lab workshop where we develop all of our lab projects. This lab project, or section of lab projects, is add-on instructions. They were a long time coming, and what held them up in delivering this, making this available, was the revision control. Because you need to understand what an add-on instruction is. If you use an add-on instruction in a program and you're using an instance of it, so it's a class of objects, and then there is instantiation or instances of that class of objects. So if down the road you alter that class of objects, all of the previous uses don't inherit those changes. Now, if you edit it in that same project, then you could do some inheritance. Meaning, if you create an add-on instruction and you use it in a program and it goes out to some customer in their machine, and then back at the shop you modify or edit that add-on instruction, those edits and modifications only exist on your computer and with the projects that you do going forward. It doesn't change the ones that are out there. So what's out there has a revision level on it, because if you go out to work on that customer's machine and your laptop that you go out there with has that add-on instruction with edits that don't exist in what was downloaded into that machine, then you've got a problem. So the software has to be able to recognize when you're connected up and doing things that, hey, the add-on instruction that you have in your project folder, or I should say in RSLogix Studio5000, does not match what's out there. So when you upload the project or you go online with it, you could run into some issues. So the revision control had to be dealt with before they would actually start shipping licenses of RSLogix 5000, Studio 5000 with the add-on instruction features. Other than that, they're real straightforward. So let's jump in and do the first section of the add-on instructions. The PLC Professor presents add-on instructions driven by the Logix engine. When to use an add-on instruction. When to create one. When to create an add-on instruction. Complex instructions tend to be highly application specific and not reusable, or require extensive configuration support code. As with the built-in instructions, add-on instructions need to do one thing, do it well, and support modular coding while reducing interdependence. Consider how the instruction will be used and manage interface complexity for the end user or application. Add-on instructions are best at providing a specific type of functionality or device control. If you work in this industry a lot, you will see a lot of abuse of add-on instructions. A high level of convolution, very difficult to follow, especially trying to troubleshoot backwards from an output that's not coming on. One of the advantages, major advantages of an add-on instruction is encapsulation. Add-on instructions are designed to fully encapsulate the code and the data associated with the instruction. The logic inside of the add-on instruction uses only the parameters and local tags defined by the instruction definition. There is no direct programmatic access to controller or program scope tags. This lets the add-on instruction be a standalone component that can execute in any application that calls it by using the parameters interface. It can be validated once and then locked to prevent edits. Programming languages for add-on instructions. Select the programming language based on the type of application you are developing. The rules are the same that you would use for selecting the language for a subroutine. Each of the languages has a very specific advantage in certain applications. So you can pick ladder logic diagrams, function block diagrams, or structured text. Sequential function charts you cannot use inside of an add-on instruction. Each of the program languages supported in the Logic Designer application is targeted for different types of applications and programming styles. In general, ladder diagram executes simple Boolean logic, timers, and counters the fastest. Function block diagrams and structured text may be more efficient if you take advantage of the more advanced process and drives instructions available in those languages. You cannot compare execution times for the same add-on instruction written in different programming languages. There are fundamental differences on how the different languages execute and are compiled. Instructions used in add-on instructions. Some instructions execute or retrigger only when the run condition in toggles from false to true. These are transitional relay ladder instructions. When used in add-on instructions or in creating an add-on instruction, these transitional instructions will not detect the rung-in transition to the false state. When the enable bit is false, the add-on instruction logic routine no longer executes. Thus, the transitional instruction does not detect the transition to the false state. Extra conditional logic is required to handle triggering of transitional instructions contained in an add-on instruction. Some examples of transitional instructions include one-shots, message instructions, PXRQ and SRT, and some of the ASCII instructions, as well as some of the motion instructions. The enable in false routine can be used to provide the conditioning required to retrigger transitional instructions contained in the add-on instruction. However, this method will not work for calls to this add-on instruction contained in a structured text routine, since enable in is always true for calls in structured text. Now, I know that was a mouthful. The warning is, for some of those instructions I mentioned, you need to do a little thinking before you use them in an add-on instruction. And then add-on instruction size. Add-on instructions have one primary logic routine that defines the behavior of the instruction when executed. The logic routine is like any other routine in the project and has no additional restrictions in length. The total number of input parameters plus output parameters plus local tags can be up to 512. There are no limits on the number of in-out parameters. However, limit extended properties, @min, @max type syntax should not be defined as an in-out parameter of an add-on instruction and should not be used in add-on instruction definition logic or the logic does not verify. Limits cannot be accessed inside add-on instruction logic. The maximum data instance supported, which includes inputs, outputs, and local tags, is 2 megabytes. The data type size is displayed on the bottom of the parameters and local tags tab in the add-on instruction definition. Again, that was more details than you can memorize by listening once. You need to go to the manual for add-on instructions and review these details. Most add-on instructions are not that large. If you feel that your add-on instruction is growing in complexity and size, you better read the limitations very closely. Also, runtime editing of an add-on instruction. Add-on instructions can only be edited offline. I guess that's all there is to say. If the intended functionality needs to be changed in a running controller, Consider carefully if an add-on instruction is suitable. So it's not a matter of anything other than you cannot edit it in runtime. When I say runtime, I also mean in the program mode. Add-on instructions can only be edited offline. Now there's a good reason for this. And it doesn't even matter what the reason is, it's just the way it is. Also, nesting add-on instructions. Add-on instructions can call other add-on instructions in their routines. This provides the ability to design more modular code by creating simpler instructions that can be used to build more complex functionality by nesting the instructions. The instructions could be nested to 7 levels deep, very similar to the depth of nesting subroutines. TIP, the enable in false routine, can be used to provide the conditioning required to re-trigger transitional instructions contained in add-on instructions. However, this method will not work for calls to this add-on instruction contained in structured text routine, since enable in is always true for calls in structured text. Add-on instructions cannot call other routines via a JSR instruction. You must use nested instructions if you need complex functionality consisting of multiple routines. In the industrial controls world, there are many things to control. One of them is motion, and the simplest is to position back and forth, in, out, insert, and remove type motion. Simple two-position control. This is normally accomplished with a pneumatic cylinder. There's a piston that can travel back and forth. There is a piston that can travel back and forth inside of a cylinder that has a port on each end. Compressed air applied to one port forces the piston to extend the rod connected to it. Compressed air applied to the opposite end of the piston causes the cylinder to retract the piston. So you have a piston and a cylinder. We typically refer to these as cylinders. So when we say pneumatic cylinder, we're really talking about a piston inside of the cylinder that has a rod connected to it, and that rod transfers the motion of the cylinder to whatever you've attached it to. Now, I know this is very sophomoric. Most people watching this already are well familiar with cylinders, but for the novice, I include a little extra. Taking a closer look at this photo, there are 2 sensors attached to the cylinder, one at each end of the travel. More appropriately, we say each end of the stroke. Cylinders are normally specified in the piston diameter and the length of the stroke. Each of the sensors has a status LED. If this is illuminated, the sensor has sensed that the piston is in that position. The sensors are installed in the correct location to sense the position at each end of the travel or stroke inside the cylinder. If there is no external limitation to the stroke, then the stroke is going to be limited by the space inside the cylinder. In many cases, you might have a cylinder with a 4-inch stroke, but you have hard stops that are adjustable for extend and retract. That's why these sensors are mounted in, if you want to call it, grooves or channels on the side of the cylinder. So you can slide these sensors back and forth in that slide, in that slot, and then tighten them, lock them down, so they actually are sensing the positions that you want. There's our application, and here's an example code for the diagnostics. So we have, in this case, we're only showing the code for one motion, and that's for extending. And you see the very first instruction, cylinder extend solenoid. And this is diagnostic. This is not control logic. Typically, when you're doing a project with air cylinders, it would be nice to include some diagnostics and put the status up on the HMI, the human machine interface. Most of the time, though, since it went to the lowest bidder did not include any hours for doing this kind of logic. If you could create an add-on instruction with the primary code already there, you're not really adding any real expense when you add this diagnostic capability. However, it does give you a competitive advantage. So let's look at the logic. Now this logic is written in what I call sequential instructions, meaning that it doesn't follow electrical characteristics. As you can see, I have a true if on, TON, true if on, OTE, one shot, and a move. If this were an electrical circuit, the extend, OTE, and the move are considered output instructions or loads in typical electrical description. So I'm using sequential code here to shorten or reduce the number of total instructions. So the very first true if on, cylinder extend solenoid, that's actually monitoring a bit that controls the output to the solenoid valve that shifts the spool to extend the cylinder. If we are telling the cylinder to extend and we have reached the cylinder extend switch, then we start a timer that's set at 200, that'd be 0.2 of a second. And when that timer is done, we turn on a bit that says the cylinder is extended. At the same time that we declare the cylinder extended, by the way, the debounce is if you have cushion, or even if you have some external hard stop that has a little bounce in it, we don't want to provide the rest of the logic an input that flickers on and off a couple times before it settles down. So the debounce timer is not totally necessary. So you could just drop that right down to a preset of 0 or 1 if you really don't need the debounce. But the debounce is there just in case you need it. So once we turn on the bit that says extended, then we one-shot the move instruction, which grabs the accumulate value, because that TON, extend switch debounce, has not seen a false transition yet. So the accumulated value is still there. So we one-shot, we capture that accumulate value and put it in another register called extend ET, elapsed time for extending. If extended is not true yet, so we're dropping down to the second branch. So if we have not extended yet, then we start a 2-second timer. Now 2 seconds is based on one particular application. So this cylinder extending timer on delay data set should have a preset value that's at least 150%, if not 200%, of the time it takes for that cylinder to extend when the system was commissioned. Because you're capturing the extended ET in the first branch, you know how long that cylinder takes to extend when you commissioned this machine. You increase that value and put that in the cylinder extending preset. Because if that timer in the second rung times out, then it has taken way too long to extend, and the extended bit doesn't come on until after the timer is done, and it latches in the extend fault. However, if the cylinder extends in the appropriate amount of time, then the extended bit goes on, the second rung or the second branch is false, and that TON never times out, and you don't latch on the extend fault bit. Also, to allow you a warning if the cylinder is starting to get slow, sticky, dirty, etc. Instead of waiting for it to take too long and faulting, we are first we're checking to see that the accumulate is greater than 0. If it is greater than 0, then we are multiplying the preset by 0.75, 75% of the preset. So you declare that, in this case, I declared that 2 seconds, 2000 milliseconds, is way too long for that cylinder to take to extend, and I want a fault if it takes 2 seconds or more. I'm calculating 75% of that preset. Now I do it this way, so if you want to reuse this instruction, whatever preset you put in for cylinder extending, this automatically calculates 75% of that. That value then becomes the extend warning elapsed time, and then right below that you see that if the actual accumulate of the timer in the second branch is greater than the warning, then it latches on a bit that says extend warning. Now that doesn't fault the machine, because in this case 75% of 2000 would be 1500, 1.5 seconds. So if it took 1.6 seconds to extend, it's not going to fault, but it is going to latch on the warning. So on an operator interface, you can have a yellow indicator that says slow cylinder. And when you touch that indicator, it's a push button or a multi-state indicator, push button with multi-states, it says slow cylinder, you touch it and it takes you to the screen that shows all of the cylinders, and then you can identify which one was slow. Now, you don't have to stop the process, but you can keep an eye on that cylinder to see if something's bent, it's dirty, or sticky. If you're not familiar with the sequential instruction programming, this is standard ladder logic format, and it is identical logic to what I just showed you, but it's in the standard format. So if you want to pause the video and study this for a minute, and then maybe go back and look at the other one a couple times, it will come to you. Also, here we have both extend and retract functions together. So these can be inside of one instruction, and typically they would be. Now if you look through here, the only values that you actually need to bring in are when you're calling for an extend or retract. So cylinder extend solenoid, cylinder retract solenoid, those would be two booleans brought in from outside the instruction. You would also need the extend and retract switch. See, cylinder extended switch, cylinder retract switch. Those two booleans would also have to be brought in. So all this logic really functions on those four parameters coming in. And then of course going out would be extend, warning, and fault, and retract, warning, and fault, as well as the extend and retract ETs if you want to put those up on the screen for the operator to look at. We had to create a new project, name it cylinders. Some of my project names, routine names, tag names may vary from time to time with what was in the manual, but the procedure and the concepts are identical. So here we have a new project, and you can't see the title bar because I have that stretched outside of the viewing area, but you can see cylinders. I do that so I can get a little bit more space in here for showing code. You can also see that I have the bottom of the window drop down so you can just see the tabs in case we want to click on those. So the first thing I had you do was create an add-on instruction after you created your project. So you go to add-on instructions, new, add-on instruction, and we gave it a simple name, CYL for cylinder. You could make it CYL, then uppercase D, lowercase IAG, cylinder diagnostics if you want. I kept it simple. I gave it a name, and I want ladder diagram. Now you see that sequential function charts aren't even present in your choices. So we want ladder diagram. And notice that we have a major and a minor rev level as well as extended text. We may discuss this later on. So remember that you're creating a class of objects that's going to be in this group down here. It's an add-on instruction, but you're going to have add-on defined as well. And these are classes of objects. These aren't instances. Think of an add-on instruction as having a program in it, and the program has a major and a minor rev level. As you import, export, and reuse this add-on instruction, it is important that you keep track of the major and the minor rev level, because let's say you created 10 projects over a couple years using your add-on instruction. And as you went along, it occurred to you that you could add another feature to the add-on instruction. Well, in that program, that project, whenever you change the class of objects over here, everything in your actual application, all the instances, inherit the changes. But in the other programs you've already done, they don't inherit the changes. That's why you have to have you have to have revision control. Let's just leave it at that. So then we went to parameters, said okay. Then we went to parameters, and we talked about these two. Now the general tab contains, which we just looked at, the general tab contains the information you enter when you first create the instruction. You can use this tab to update that instruction. The description, revision note, and vendor information is copied into the custom help for the instruction. In other words, you can create custom help information for each of these instructions, help for you using it in the future in case it grew cold in your head. The revision is not automatically managed by the software. You are responsible for defining how it is used and when it is updated. Now we'll take a superficial look at each of these tabs. Parameters and local tags are used to define the data type that is used when executing the instruction. The software builds the associated data type. The software orders the members of the data type that correspond to the parameters in the order that the parameters are defined. Local tags are added as hidden members. The data type for a local tag may not be a multidimensional array or an object type, which includes all motion types: message, alarm, analog, alarm digital. The data type field is unavailable for members of a local tag. The parameters define the instruction interface. That is, how the instruction appears when used. The parameter order defines the order that the parameters appear in the instruction call. An instruction with only input parameters, except for the enable out, is treated as an input instruction in a ladder diagram and is displayed left justified. The enable out parameter is used for the rung out condition. You can also designate a parameter as an alias for a local tag by using the tag editor. Check the box at the bottom of the add-on instruction definition editor to copy all default values of parameters and local tags whose values are modified to all tags of this instruction type. If you want to update the existing invocations of the instruction to the new default values. You can also create parameters by using the tag editor, new parameter or local tag dialog box, or by right-clicking a tag name in the logic of your routine. Local tags. The Local Tags tab defines tags that are used by the logic within the add-on instruction and are not visible outside the instruction. They are local tags. Just as the program tags are only accessible to the code in that one program, not to the other programs in that task, the local tags are only available to that instance of that instruction. They're not available to other instances of the same add-on instruction. So this gives you another level of granularity, much finer, of encapsulation of your tags in your control. The only way to make a local tag or one of its members accessible from outside the instruction is by defining it an alias parameter. You can access local tag values from an HMI by specifying the name of the local tag as a member of an add-on instruction or type tag. In other words, you can specify the name of the local tag as a member in an add-on instruction type tag. In RSLogix 5000 software, version 18 or later, you can choose to copy parameter or local tag default values to all tags of the add-on instruction data type or just to specific tags. You can do so only when you are offline. Values cannot be modified when the instance tags are part of a source-protected add-on instruction, or if you do not have sufficient permission to make those edits. If you do not define an optional scan mode, the following default behavior before an add-on instruction occurs. So we're not going to discuss all these scan modes, not at this level. Maybe we'll say that for volume 3. Provide add-on instructions with the same flexibility as built-in instructions. Remember, we talked about transitional instructions don't sense the change in the enable in to the add-on instruction. However, to give you the same flexibility that predefined instructions have, optional scan mode routines can be configured to fully define the behavior of the instruction. Scan mode routines do not initially exist for add-on instructions. You can create them depending upon the requirements of your instruction. Like all built-in instructions in the controller, add-on instructions support the following 4 controller scan modes. Signature. The instruction signature consists of an ID number that identifies the contents of the add-on instruction and a timestamp that identifies the specific date and time at which the instruction signature was generated, or a signature history entry was made, whichever came last. Once generated, the instruction signature seals the add-on instruction, preventing it from being edited while the signature is in place. In addition, when a sealed safety type add-on instruction is downloaded for the first time, a SIL3 safety instruction signature is automatically generated. The safety instruction signature is an ID number that identifies the execution characteristics of the safety add-on instruction. The signature history provides a record of signatures for future reference. A signature history entry consists of the name of the user, the instruction signature, the timestamp value, and a user-defined description. Up to 6 history entries can be stored. If a 7th entry is made, the oldest entry is automatically deleted. The Change History tab displays the creation and latest edit information that is tracked by the software. The By fields show who made the change based on the Windows username at the time of the change. An add-on instruction is executed just like any other routine belonging to a particular program. Because another task can preempt a program containing an add-on instruction that is being executed, an add-on instruction may be interrupted prior to completing its execution. In standard programs, you can use the user interrupt disable enable UID UIE instructions to block a task switch if you want to be sure the add-on instruction executes uninterrupted before switching to another task. The name, revision, description, and parameter definitions are used to automatically build the instruction help, using the extended description text to provide additional help documentation for the add-on instruction. This content reflects updates as parameters or other attributes are changed in the definition. The instruction help preview shows how your instruction will appear in the various languages based on parameters defined as required or visible. Now, we don't have any real help defined right now, so whatever is here is based on what we have so far. We haven't added any ladder logic, so we don't have any parameters to speak of. There's really nothing to look at. So we'll click OK. That really completes the creation of an add-on instruction. So now when you look at add-on instructions, you see a plus sign there. If you open up the logic, of course, there's nothing there. If you open up the parameters and local tags, there's only enable in and enable out because we haven't actually added anything yet. If we go to add-on defined, you see the same structure there as this. We'll go back and look at this again once we've actually added something to look at. Now let's add some code to our add-on instruction. We go over to Cylinder under Add-on Instructions, Logic, and open it up. Now this looks like you're in a routine. In a sense it is a routine, but it's a class of objects routine, meaning it's the template or the definition for that add-on instruction in terms of logic, but it's not an actual instance. So this will never be executed from this location. You will create an instance of this instruction, give it a name, and that instance will be executed, but never the actual class of objects over here under add-on instructions. We have our logic open for the add-on instruction cylinder. We're going to add some code. Rather than making you watch me type all this in, I'm going to add the basic logic and then come back. I'll just do a brief bit of code entry for those of you that are new. Typically what I do is I start with an empty rung, and then I just start typing in instructions. I need an XIC space BST space TON space XIC space OTE space ONS space MOV. Enter. Now this was the branch start, which automatically gave me a branch end. So if I double click, you can see that by adding a branch start, the move was the last thing I typed in. I automatically got a next branch, which is this, because you can't have a branch start without a next branch, and you can't have an NXB next branch without a BND branch end. So then if I go to here and double click, I'm excluding this text entry here. Now I'm just working on this second branch. So I got an XIO space TON space XIC space OTL. Enter. Right click, add branch level, and I have a GRT space BST space MUL. Enter. And here I have a GEQ space OTL. Enter. So there I have all of the logic in, but no tag names. For those of you that aren't accustomed to entering the code in by just typing in the 3-character acronym or mnemonic for the instruction, that's an XIO, that's an XIC, OTL, OTE. Some of them are obvious, ONS, MOV, some of them are not. So I'm going to pause now and type in some tag names. Okay, I have a few tag names typed in, but they're not actually defined yet. There's a reason why we did not define them in the usual method. We'll go to the first one here, cylinder underscore extend solenoid. Right click, and this is going to be a parameter. We don't want this to be a local tag. We want it to be a parameter because this is actually the state of the bit that controls the output, that controls the extend end of the solenoid valve. So this is external to the add-on instructions. So we go to new parameter. The name's already in there. We want to select input parameter, base, Boolean. Now input parameter is already selected. I'll drop down the list so you can see that there are more. We wanted input parameter, and then we click OK. This is now defined as an input parameter for this class of objects named cylinder, which is a add-on instruction. Then we go to the next one. Well, it looks like I forgot one. Go back and look at my logic. Yes, I did. I needed an XIC right here. So I'll pop that in there. And that should have been cylinder extend switch. And I'm going to make it extended switch, even though that's not what I had. Oh, I guess I did do that in the manual. Cylinder extended switch. We right click on this. This is also an input parameter. Remember, this is looking at the output bit that controls the solenoid valve. This is actually looking at the proc switch. So new parameter, input parameter base Boolean, click OK. Now we have those two tags defined, but they are actually, you can call them tags or you can call them parameters. Now we're going to go to the timer, the extend switch debounce. This, however, is going to be a new local tag. And it already has timer, local tag, so it's kind of intuitive or type forward. When doing this type of tag work, remember that some tags are members of a data type that has many members. Always first define the primary tag, and all of the members of that tag are then defined as well. Now in the manual I had you type in all of the members for the timers. You see I left them out here because I wanted to try something different. If you tried to define it first, it would have given you some serious challenges. In other words, if you had defined these outside, whenever you see a delimiter in a tag name, it is a member of a primary tag. In other words, you can't define extend switch debounce. Now this is a timer. You can't define the accumulate or the done bit or the timer timing bit before you actually define the actual tag structure itself. I guess that's what I was saying. Click OK on that one. Now if we mouse over here, so I had you mouse over here, but there's nothing in there. I'm going to take and drag this up to there. I'm going to double click, and I could either type in .dn or I can open up and double click on it. See, and that's shown as a Boolean data type, local tag, tag data type timer, and we'll go to the next one. This was cylinder extending. We haven't defined that one yet, so we'll define this one. This is a local tag, local Boolean. Okay. This is a local tag, local Boolean. So this is now defined because we defined it right here. This, however, is a new local tag. It's a timer, local tag. Click OK. Now we can drag this to here and put in .dn. See, the minute I put in the D and the N pops up, uppercase, reverse video. That means it knows it. This is undefined. Now the default, we want that to be an output parameter. This extend ET, if we want to be able to view that and work with it outside, then we need to define it as a new parameter, have it be an output parameter. If we want this to be an output parameter, up here we wanted the cylinder extending accumulate, so we can drag this up here, double click on it, and then type in decimal point ACC, enter. And you see now that's a happy tag. We'll stretch this a little bit over. I don't like working with wrapped around rungs. So we have most of this defined. This was going to be cylinder extending preset. So you can drag this one or this one, it really doesn't matter. We'll drag this one down. Double click. .pre. Now you notice that that's a defined tag, and we want it greater than 0. Then we want to multiply this preset by 0.75. This could actually be either, but it's the actual value where you receive a warning. So we're going to make that a local tag of the dent type. And then we want to take the cylinder extending ACC, notice we still got E's over here in our edit zone. And here we need retract warning. I'm sorry, extend warning. EXT_WARNING. And we want to define this as an external, so it's going to be a parameter, output parameter. Now you see the e's disappeared because it's happy with everything inside of the rung. Now that you have this rung completed, you're going to click on this rung. You're going to do Control C, Control V, and that puts a copy of it right below it. So now you have two identical rungs. In the second rung, I told you to be very careful not to edit any of the existing tags. If you go up here and say Edit, and you change this to Cylinder Retract Solenoid, then it's going to change it in both rungs. We don't want to do that. We want to type in. So don't right-click and edit. Just type in Retract. And as soon as we do, watch over here in the edit zone. See, the E's pop up because that is an undefined tag. So we go over here and we edit the text, but not the tag. Sometimes it's easier to just type in the tag name rather than editing the text of the previous tag name. I like to use as much of the prior that I can just to keep everything looking consistent. Now this one we've already put in, so I can drag it down to here. This one is cylinder retracting. Now this tag right here is going to end up being a member of this tag. By typing these in separate, you always take a chance on a typo, fat fingering one of the characters. So this might define and that not, or if this was wrong, it will probably define anyway, but this will never show up as a member of that tag. So it's up to you how you want to edit the text. And really, I don't put a lot of effort into making sure that I get everything typed in perfect. Because it all comes out in the wash. Now let's define these. This, remember, is an input parameter. Input parameter Boolean. This is an input parameter. Whoops, that's already defined. I was on the wrong one down here. This is an input parameter. This is an input parameter. See, you got to be careful because I'm working on this rung, but that it popped back to the head of the class here. That's a very irritating characteristics of RSLogix 5000. So right click, local tag, timer, local tag. And of course that is automatically defined. See, we defined retract switch debounce, and this was automatically recognized as a member of this data type over here. So this is a Boolean, and it can be a local tag. This is a local tag. Now, we really don't want to define this until we define this one. So we'll define this one as a timer local tag, and that will automatically define that one. This is, we're going to make this an output parameter simply so you can view it outside the instruction if you want to view it on your HMI. Retracted is already defined. We defined it up here. We already defined this in order to define this one, and notice this is also defined, so we need to define this one, and this is an output parameter because we want to be able to use that fault bit external. This is already defined because we defined it right here. This is defined, this is not, and this is, we're going to make it an output parameter. Now you see the E's are gone. So we have two rungs here. One is the diagnostics for extend, the other is the diagnostics for retract. Well, we have some latched bits here for what I see when we did not change. And the reason is because when we got to a certain point, there was a tag left that had not been changed from the upper rung, but it was still defined, therefore the E's disappeared. So watch out for that. So you go through here real quick, retract, 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 one shot, two, retracting, retract, retract, retracting, retracting, retracted, retracting, retracting, retract, 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 retract. Okay. Still, this isn't defined here yet. And this is a output parameter. Now the E's will disappear again. To unlatch these, we're going to add another rung with 4 unlatch UTLs. This is going to be called reset. And this is going to be an input parameter because we have to reset it from external to the add-on instruction. So we'll have to have something that externally does that. Now see if I can drag this down, and I'll put the retract warning in front of the retract fault. And I can see that I can't drag this all the way up and have them both in view. So I'll just type in ext underscore w. There's the warning. ext underscore, that's et. Type in an F, and then we have our fault. Now you see we have an external method from this input parameter. We can unlatch any of those bits. Remember, the instructions are in the bits are part of the instruction, so you don't reset them with logic external. You have an input parameter that unlatches them internally. Okay, save your project. Open your main routine. Once it's saved, so we go to the main routine, open it up, and we're going to go to our add-on instructions right there. We've only got one. We need a rung, of course. Drop in an add-on instruction, and we'll call it cylinder 1. So even though you might think it's automatic, that if you picked a cylinder add-on instruction, you gave it a name, it would automatically be defined. Well, no, you still have to define it. In the lab book, I ask you, what is wrong with this picture? Where are all of the input and output parameters that we created? Well, we didn't make any of them visible. So next, we're going to right-click on our actual add-on instruction over here, and we're going to select Open Definition. And then we're going to go to parameters. I'll stretch this out a little bit. And we need to mark some of them visible. Some of them are required and visible. We'll go down and we'll check. We need our solenoid and our switch. And notice if you make it required, it's automatically visible. We also want the fault and warning to be visible. The reset is required. So I believe that takes care of everything. Now I have a few more than that selected. I have the extend ET and the retract ET also selected in the lab book. So rather than deviating from what I had you do, this is good because I want to show you how to make them more readable. So I'll go back over here. This is the object, the class of objects. That's not the instance. Any changes we make here will be inherited by all the instances that we have in Logix. So I'm going to go to Add-on Instructions, Cylinder, Open Definition, go to Parameters, and I can take and move them around. See the move up, move down? So on top I want Cylinder Extend Solenoid. So I go, and it is on top, and then I want Cylinder Extend Switch, and then Extend ET. So those three are in the right order. Then I want the warning, then the fault. So I'm going to click on this one and say move up. So warning comes before a fault. Then I want cylinder retract, solenoid, cylinder retracted switch, retracted ET, and then I want extend or retract warning. So I pick this one, move it up under retract ET, then I want retract fault, it's in the right place. And then I want cylinder extend solenoid switch, that's good. Stretch this out a little bit. The warning, this I should move all the way up, either here or at the end. So this is the beginning of the retract, solenoid, retract switch, ET, and then the warning in order to make it match the upper set. See, extend warning, then the fault. The retract ET comes right after the switch, right there. Remember, this is extend and this is retract. So solenoid switch, ET, warning ET. See, extend ET, extend warning ET, retract ET, retract warning ET, then warning and fault. And then, of course, resets, there's only one of those. It's not an extend or retract, it's just a reset. So you see you can move these around. Now watch over here. See, these were all out of order. When I hit apply, it's going to come up and say, are you sure? Yep. Now, these are in a more readable order. The run was happy before we required all these parameters. Now that we've required these parameters, they have to be associated with a tag outside of the instruction. Okay, now I've added the logic. I also took the liberty of aliasing some of these tags to actual I/O. Another thing I did was when I recorded the earlier part of creating the add-on instruction, I did something slightly different than I did in the manual. Maybe you noticed, maybe you didn't. So what I had to do to what I had created earlier is I had to go back to the add-on instruction, open the definition, open the parameters, and I changed these two tags right here. They were local tags. They were in this group. And in the manual, I had you do it this way. But in the recording, I, without thinking, made these two local tags instead of parameters. In this case, output parameters, because we want these 2 bits available outside of the add-on instruction. Otherwise, one feature of the add-on instruction won't function correctly, and I'll explain that. Here's where those 2 tags are used. In order to simplify the ability to demonstrate this add-on instruction, and let me emphasize something very strongly. This is not about using add-on instructions. This is about creating add-on instructions. We've already created the add-on instructions, so at this point we're doing a superficial demonstration of the add-on instruction. And if you look here, these are the 2 bits that really trigger the add-on instruction. If we open up the logic, we can open up the class of objects here, or we can go right click here, open instruction logic, open definition. If you open the definition, then you can open up the logic from here as well, so you can look at everything. However, typically I just right click on the add-on instruction, open instruction logic. This bit right here, the extended and the retracted. The way we're using the extended switch and the retracted switch is we have a debounce timer. And the debounce timer, I have it set at 2 seconds, and that's only so you can actually observe it accumulating. In reality, it would be set to 1/10 of a second at the most, to 100. As a matter of fact, I'm going to bump this up to 10 seconds. That way when we're running this, we have some time to watch it. If this were set to the actual realistic values for the debounce and the extending and retracting timers, it would go too fast. The update time between the controller and the screen is just not good enough for you to actually see what's going on. Another thing that will be noticeably odd when we execute this logic is when we actually do turn on the extend switch and start this timer, if with it set at 2 seconds, this timer is still going. In other words, if we tell the solenoid to extend, to shift the spool, to shift the cylinder, until this bit goes on, which means this goes off or false, this thing keeps right on timing, and you're timing towards a fault. So this 2 seconds is the first 2 seconds of this 10 seconds. But in reality, this would be 1/10 of a second, and it would be unnoticeable. You would hardly notice the difference between the switch being made and this bit coming on. Nonetheless, this extended bit and this retracted bit, we need those out here to extinguish the solenoids once the switches have arrived. Now, in the real world, you would probably have some other method of controlling that solenoid, but for all practical purposes, we'll say that this is a dual solenoid valve body controlling a single-ended cylinder, and the configuration of the valve body, it's dual solenoid, but it's spring return to center, all ports blocked. What that means is when you power one of the solenoids, it shifts the spool and applies pressure to one side of the cylinder, of the piston, and it either extends or retracts depending on which solenoid you energized. When you de-energize a solenoid, a spring returns the spool to its center position and blocks all ports. That way it kind of holds the cylinder in position. It doesn't allow the pressure to dissipate inside of the cylinder. In order to accomplish that, so you can do a momentary push button here and then have this bit seal in the code so the solenoid continues to apply pressure until the switch is made. In order to accomplish that, we had to bring the extended and retracted bits from the add-on instruction out to this logic. That might not ordinarily be necessary because how you control your auto extend. Now this is manual. Auto extend, this bit is just there to represent a connection to the auto sequence that doesn't even exist. But this is what you would see typically when you're looking at code. They put all the outputs in one routine, and then for each output they have a manual condition and an auto condition. Then of course these are safeties, cylinder 1 OK to extend, and then the fault, which comes from the add-on instruction out to extinguish the solenoid just in case it's taking too long to extend. It stops trying after whatever the fault time is from the add-on instruction. In other words, I had to go change there was something that was a local tag, and I made it a parameter, and that were these two tags right here, extended and retracted. That way I could pull those out and use them externally in Logic. We're going to conclude part 1 right here. Take a pause for the cause. And we will come back. We've already gone a little over an hour. We'll come back and continue right where we left off with our add-on instruction cylinder application. Thank you. Look for part 2.